Welcome back, my dear students. Welcome to the second part of the video for 4.8. So in the first part, we looked at some word problems involving directions and bearings and navigation. And in the second part, we're going to look at harmonic motion. Now, the goal in this class in pre-calculus is not for me to explain to you all the science, although if we were in person, I'd spend some time doing that. But I'm going to focus on the mathematics of it. So I'm going to focus on the graph of the harmonic motion and how it relates to the equation of the harmonic motion. Just to make sure you guys have a basic, simple idea of what harmonic motion is. Basically, anything that moves, any particle or, yes, any particle or anything that moves in a sinusoidal fashion. In other words, it does a sine curve. It's called a sinusoidal curve. It does what is called harmonic motion. Let me give you a very brief illustration. Here's an oscillation of harmonic motion. This thing, something on a spring going up and down, will model basically what harmonic motion is. Waves of the ocean do this. Any kind of wave does it, in fact. Oops, let me go back to that. Any kind of wave does it. Radio waves, microwaves, any kind of wave does this kind of thing. It's called harmonic motion. Okay. So we're going to look at the mathematics of it, and Dr. Bauk in physics, he can explain to you all the physics around that. All right, back to the math. Okay, so let's see. Mathematical definition of harmonic motion is this. A point that moves on a coordinate line is in simple harmonic motion when its distance d from the origin is given by either of these two equations. Now, we looked out in the meets, the sine equation and the cosine equation. They can be the same thing depending on where it starts. But I hope that you recognize that this is simply y equals a times the sine of bx. That's all it is. We're just using a and b to transform the parent function. Or d equals a times a cosine of bx. Although instead of using b, they're using omega. That is a Greek letter. It looks like a W, but it's actually the last letter of the Greek alphabet called omega. They point out here that a and omega are real numbers, and omega has to be positive. Of course, omega has to be more than 0 because, as you know, that b, or that omega, tells you how many cycles are in 2 pi, and you can't have negative number cycles in 2 pi. It also points out that the motion has an amplitude of the absolute value of a. You knew that. The amplitude right there is a. You know that the period is 2 pi over omega because in our previous lesson, we said that the period was 2 pi over b. Now we're replacing b with omega. Oops, hang on a second. I got to turn something off here. Go away. Sorry about that. All right. And then it has this thing called frequency. I'm going to come back to frequency in a second. I'm going to come back to frequency as we do this example. So we're going to do 2 examples. Here's the first one. Write the equation for the simple harmonic motion of the ball below. Its period is 4 seconds, and its maximum distance from equilibrium is 10. In other words, this distance right here, aka the amplitude, is going to be 10. That's its maximum distance from equilibrium. Equilibrium is right here. So it bounces up, then it bounces down, then it comes back to equilibrium, it bounces up and bounces down, and so on. Its momentum carries it. And it tells you that the period is 4 seconds. So this distance, well, not this distance, but this time is 4 seconds. This will be t, and this axis will be d. So the distance in a vertical direction over time. All right, so we need to write an equation. So first of all, I'm noticing that it starts here. So I'm going to go ahead and call this a sine instead of a cosine. Cosine starts up there. So I'm going to say that the distance equals, I'm going to have a sine there. I know the amplitude is 10, therefore I'm going to go ahead and put a 10 right there. Now, the period is 4 seconds. So this is going to be a little bit tougher to do, but I'm just going to use this equation. So using this equation, if you know that the period is always going to equal 2 pi over omega, and you know that your period is 4 seconds, I'm going to plug in 4 for period, and I get 4 equals 2 pi over omega. Cross multiplying, I get 4 times omega equals 2 pi. Dividing by 4 on both sides, I get omega equals pi over 2. And therefore, I'm going to use this equation, and I know my omega value is going to be pi over 2 times t. And therefore, that is going to be my equation. Now, let's go ahead and verify that this makes sense. The 10, I know that makes sense, you guys. This pi over 2, this should be none other than the number of cycles in 2 pi seconds. Let's see if that actually works. So pi over 2 is approximately, what is pi divided by 2? It's about 1.5, more or less. So are there 1.5 cycles in 6 seconds? Let's see. So I know this is 4 seconds, so this is 6. So 6.28 seconds. This will be 2 pi seconds. And you tell me, does there seem to be about 1.5 cycles there? Yeah, see? So this number still does describe the number of cycles in 2 pi seconds. Or if you want to be precise, we could just call it pi over 2. So the equation is d equals 10 times the sine of pi over 2t. All right. Hopefully that one was okay. Let's go to the second example. What's it tell us to do this time? Consider the equation of the simple harmonic motion given by this equation. D as a function of time equals 6 times a cosine of 3 pi over 4t. All right. Find, and please be looking at the while. What did I just write there? I think it says be looking at the graph. I don't know what happened. Please look at the graph while you're doing this to make sure that you can understand what's going on. Yeah, I don't know what happened there. All right, so it's asking you for the maximum displacement. So the maximum displacement is this distance here, the distance from equilibrium to either the top or the bottom. So that's easy. Your maximum displacement is 6. It doesn't give us units, so 6 units of whatever it is. Science teachers would be furious if I didn't put units. Don't tell the science teacher that I didn't put units on this. Find the frequency as well. All right, find the frequency. Oh, that's the one I talked about earlier. I said we'd come back to it. So let's take a look at the equation for the frequency. So the frequency is omega over 2 pi. And let's see what the frequency actually means. So the frequency is omega over 2 pi. Let's find it first just by using the formula. Then let's go back to see if we understand what it means. So first of all, my omega is 3 pi over 4. So that's my omega, 3 pi over 4. And then I need to divide it by that. So I'll just multiply it by 1 over 2 pi. And I get that my frequency is 3/8. All right. So let me go back to the front and give you some notes on what that is. And then hopefully you guys can relate it to the answer that we just got. Did you notice that the period and the frequency are just reciprocal of each other, right? So I'm going to come up here and write that bigger because I can't write it so small in there. We know that the period is 2 pi over w. And the units for that are seconds per cycle, right? Because w represents a number of cycles, and 2 pi in this case is my time. When it comes to frequency, the frequency equals omega over 2 pi. And so that will be cycles per second. So when we're talking about frequency, we're talking about how many cycles do we have per second. The period, on the other hand, is how many seconds is it for every cycle. So this is going to be cycles per second, the frequency. So let's see if I actually have 3/8 of a cycle per second. So let's see, 1 second is right here. And I really bombed that line. Sorry about that. 1 second is right here. And I want you guys to notice, does it look to you, this is 1 cycle, that I just marked it in blue. Does it seem to you that there are 3/8 of an entire cycle in 1 second? Yeah. So your frequency is 3/8 of a cycle per second. Or if you wanted to, you could say 3 cycles every 8 seconds. Let's see if that's true. 3 cycles every 8 seconds. So there's 1 cycle, there's 2 cycle, there's 3 cycles. 3 cycles take 8 seconds. So that is what your frequency means. How many cycles per second? All right, let's go ahead and find the value of d when t equals 4. I'll just plug it into the equation. So I'm going to plug in 4 for t. So I'm going to plug it into there and there. And I'm going to get 6 times a cosine of 3 pi over 4 times 4. All right. And when I do that, These guys are going to cross out. This is the angle right here. These guys are together. And I'm going to get 6 times a cosine of 3 pi. So let's think about a unit circle here. What's a cosine of 3 pi? So I'm starting. So here's pi, here's 2 pi, here's 3 pi. So this is the point -1, 0. So the value of the cosine here is -1. So the cosine of 3 pi is -1, which will give us -6. So at time equals 4, I should get -6 for my distance. Let's see if that's true. Here's time of 4. And what is the distance at that point? -6. Yeah, so it makes sense. That's why it's important to look at the graph to make sure that you know what you're looking at. All right, last one. What is the least positive value of t for which d equals 0? Okay, well, I can tell from the graph, or at least I used to be able to tell from the graph before I made a mess of it. But the least positive value of t for which d equals 0. So the distance 0 is along the x-axis. And the d is 0 here, d is 0 there, d is 0 here, d is 0 here. So I mean, d is at 0 a whole bunch of times. So it's asking you what is the smallest value of t. So obviously I'm looking for that. So I can estimate it just by looking at the graph, and it's about, well, that's 1 second. So it's like, it's more than half a second, but less than 1. I don't know, like 0.6 seconds, 0.7 seconds. That's going to be my estimate from the graph. And it's always good to do an estimate before you do the math to make sure your answer makes sense once you get it. So let's go ahead and figure out what it would be. Let's use the equation for it. I want to plug in 0 for d this time. So I'm using this equation and plugging in 0 for d. So I'll go right ahead and write it. So I know that d equals 6 times a cosine of 3 pi t over 4. And I want d to be 0. So one thing I can do, obviously, to both sides is just divide by 6. There's no reason I can't divide by 6. So when I divide by 6, I'm going to get... All right. So now let's think. I need the cosine of some angle to equal 0. What is the smallest angle at which the cosine is 0? Again, looking at the unit circle, right here is the smallest angle at which the cosine is 0. There he is. That's him. So at pi over 2 or 90 degrees, the cosine is 0. That's the smallest angle. There are other ones. I mean, cosine is 0 at here, and again at 270, and again at 540 degrees, and again at whatever. But the smallest angle is asking us, the least positive, it's going to be 90 degrees or pi over 2, which tells me that 3 pi t over 4 must equal pi over 2. Think about what I just did there. That was a tricky move. Okay, the cosine of this angle equals 0. So what must this angle be? Well, this angle must be pi over 2 because the cosine of pi over 2 equals 0. So I'm saying that 3 pi t over 4 needs to equal pi over 2 because that's where the cosine is 0. I can divide both sides by pi, obviously. And when I do that, the pi's cross out. And now doing a little bit of cross multiplying, I'm going to get that 2t. Oh, no, excuse me. No, not 2t. I got to be careful here. 3t times 2. I get 6t equals 4. And dividing by 6, I'm going to get that t equals 2/3 of a second. 2/3 of a second. And hey, look, my estimate was like 0.6 or 0.7. It's actually 2/3, which is 0.66666. And as you can tell, it seems to be right that at about 2/3 of a second, that is the first time that it is 0. Okay? So there is the mathematics of harmonic motion. Again, in physics, you'll learn much more about the physics of it. But when you get to those physics classes, you need to be able to deal with the math. And when your teacher writes down on the board that this is an equation that has to do with a cosine, you should have the skills to say, oh yeah, okay, I can deal with that. And that's our focus in pre-calculus. Okay, that's it. If you have questions, let me know. And again, we're going to go over some of these questions at the meets. I will see you next time. Bye.